Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out our playlists and watching our videos. And then any liking, sharing, commenting, any of those activities are greatly appreciated because it helps us to grow and it's free. So please, go ahead and help us out. What I want to take a look at in this current video is what's called the subspace topology. Now, chances are if you're watching this video, you've probably taken some courses in linear algebra, possibly some abstract algebra, something like that, meaning you have experience with vector spaces and groups and rings and fields. Now, within each one of those structures, we can talk about substructures, subvector spaces, we can talk about subgroups, subrings, so on and so forth. And what that generally consists of, or what it's going to consist of, is a subset of the main structure that also has the structure of the big set. For example, a subgroup is going to be a subset that's also, in fact, a group. Well, what I want to take a look at is what if I have a subspace in a topological space? How does that work? Well, so let's go ahead and take a look at the following. For a topological space, x tau. Okay, so if I have this topological space and I have a subset y of x, so and y is a subset of x, then basically the idea is how can I consider y to be a subspace? Then we want to see how to make a subspace out of y which is related to the topology on the big space. Okay. Well, how can I find a topology on y that is, of course, related to y? And the way that we do that is as follows. The subspace topology is tau sub y. Usually I'll just read it as tau y. Subspace topology is tau y, where we define it as follows. Tau y is equal to the following sets. What I do is I take the subset y and then I intersect it with u, where u is an element of the topology on the primary space here. So I take every element of the topology tau and I intersect it with y, and I take that whole collection of sets, put it together, and I'm claiming that is going to now be a topology on y. Well, if that's going to be a topology, we should probably first of all verify it. So verify that tau y is a topology on y. It's a pretty straightforward computation. What I'm going to do is I'm going to take elements of the primary topology tau, and we're going to then show that we can generate topology out of tau y. In particular, I know that the empty set is an element of the primary topology tau, therefore y intersect the empty set. Well, that satisfies the definition of what my tau y is. It's y intersect elements of the topology tau. And of course, this is equal to the empty set, and that, of course, is an element of tau y. Okay. Now, next thing I want to show is also that y itself is going to be inside of this tau y topology. Well, I know that y is a subset of x, so I have to be able to intersect y with something to show that y itself, so y intersects something equals y, is an element of tau y. Well, I don't know that Y itself is an open set of the original topology, but I know that X is an element of the original topology. So therefore, I'm going to say X is an element of the original topology. Therefore, when I intersect Y with X, since Y is a subset of X, this is equal to Y, and therefore that is also an element of the topology tau Y. Okay? All right. Now I have to show that this set is closed under finite intersections and arbitrary unions. So let's let, again, I have to show that this is closed under finite intersections. Let's do that one first. So let's say I've got Y intersect U sub n is an element of tau Y, where n ranges from 1 to k. Okay? I have a finite number of these things. Now, if I take the intersection from n equals 1 to k of Y intersect un, so let's group that together here. Well, by properties of intersections, the intersection of the intersections is going to be the intersection of the intersections, right? I hope that makes sense. This is equal to Y intersect the intersect from 1 to k of un. Well, if I look in the parentheses here, the intersection of the UNs, this is a finite intersection of elements of the original topology, therefore that's in the original topology, and therefore Y intersect that set satisfies the definition that I created for tau Y, and this is an element of tau Y. Therefore, the tau Y, what I'm going to prematurely call a subspace topology, right? I'm verifying that it's a topology, but then I'm also calling it a topology. But then verifying that the subspace topology is in fact closed under finite intersections. Now let's show that it's closed under arbitrary unions. Okay? And it's going to be a similar computation to what we just showed. So now let's say let Y intersect UI be an element of tau Y for I in I. In other words, capital I is any index set, could be finite, could be countable, could be uncountable, whatever, it doesn't really matter because I need this to be arbitrary. Now I take the union of all of these. So the union for I in I of Y intersect UI. Okay? And this is going to be Y intersect the union of the UIs, again, where I ranges over the arbitrary index set I. And within the parentheses here, this is an arbitrary union of UIs. Remember, UI was an element of the original topology, which is closed under arbitrary unions, meaning that this union is an element of the original topology, and therefore this is Y intersect an element of the original topology, which again is my definition of tau Y, and therefore is an element of tau Y. Therefore, Y tau Y is a topological space and is then a subspace of X tau. Okay, so this is how I create a subspace of a topological space. Now, this is just generic. Let's go ahead and take a look at a specific example. So what I'm going to do is I'm going to give you a set X, I'm going to give you a topology on that set, and then I'm going to give a subset of X, and then we will construct the corresponding subspace topology on it to see how the subspace topology is actually generated in practice and how it's related to the original set. And we'll see if we can come up with some other conclusions based on what we find. But let me go ahead and clean, well, I guess I can go ahead and start down here. So let's say my set X consists of the elements 1, 2, 3, 4, and 5. Now let's construct a topology on this. Let's say I've got the empty set, the set X, and then let's do the singleton 1. Let's do the set 2, 4. Since it's closed under unions, I'd also have to have the set 1, 2, 4. And let's add a couple more here. So I've got 1, 2, 4. Let me start it back up here. Let's say I've also got the set. Oh, there's a different color there. I guess that's okay. Let's say I've got 1, 2, 4, and 5. And let's see, that should be, yeah, that should be enough. Again, first and foremost, let's verify that that's a topology. Notice if I take unions, union of 1 and 2, 4, I get 1, 2, 4. If I take the intersection of, say, 2, 4 and 1, 2, 4, I get 2, 4. If I take 1, 2, 4, 5, take the union with 1, 2, 4, I get 1, 2, 4, 5. I take the intersection, I get 1, 2, 4. And again, there's other combinations you could check here, but you just need to make sure that it's closed under unions and arbitrary unions. But since there's only finitely many elements, it's equivalent to finite unions and then finite intersections as well. And it should be closed under those. Now what I'm going to do is let's define a subset Y. And let's say the subset Y consists of 1, 2, 3, and 5. Okay, so this right here, this set Y, is a subset of X. Now let's generate the subspace topology on that, and tau Y. Okay. So the way we do this is I'm going to take this set here and just intersect it with all the different sets of the original topology. 1, 2, 3, 5, intersect that with the empty set. Of course, I get the empty set. 1, 2, 3, 5, I intersect that with X. I'm going to get 1, 2, 3, 5, which of course is Y itself. I'll intersect 1, 2, 3, 5 with this singleton 1. Of course, I get the singleton 1. Intersect it with 2, 4. I'm going to get the singleton 2. Intersect Y with 1, 2, 4. I'm going to get 1, 2. And then if I intersect Y with the last set here, 1, 2, 4, 5, I'm going to get 1, 2, 5. All right. And again, verify. You can pause the video and verify that that's a topology. It's closed under unions and intersections, and it's got the empty set, and it's got the big set Y in this case. Okay, so therefore this is a topology, and then Y comma tau Y would be a topological space in its own right, and in particular Y is a subset of X. Tau Y is generated by the original topology. Now one thing to notice is let's take a look at an open set in the subspace topology, in particular the singleton 2. The singleton 2 is an element of the subspace topology, okay? As is these other sets, but let's just highlight that one. But then if I look at the big topology, that is not in there, okay? The singleton 2 is not an element of the big topology. So the idea is that open in Y does not imply open in X. In other words, the subspace topology does not need to be a subset of the original topology. It's going to be related, of course, because you could see the way I constructed it by just intersecting the sets. But sets here might not be sets down here. And in fact, in this particular example, the only thing that is open in both would be the empty set. Y itself is not even an element of, no, because it's 1, 2, 3, 5, that's not even an element of the original topology. Okay. Now there are cases where open in Y does imply open in X, and we can explore those in another video, but just generically speaking, open in a subspace does not imply open in the big space. Anyway, thank you for watching, and please consider subscribing.